Welcome back. So in this video, which is the last in our Math Stat 1 series, we're going to take a look at some constructed distributions, or some distributions that can be used to describe particular quantities from a sample. So we'll talk about the distribution of the sample variance. We will also, in this video, introduce the t distribution and the f distribution. Now these are sampling distributions that are all related to the normal distribution. So a central underlying assumption that we'll be making is that our population is normally distributed. So let's take a look. First, let's start with the sample variance. So let's let y1 through yn be a random sample of size n from a normal population with mean mu, variance sigma squared. If we calculate a z-score for each one of these independent standard normal random variables and sum up the z-scores, it turns out that that follows a chi-square distribution with n degrees of freedom, where n is the number of independent standard normals that we are adding together. So if we add up independent squared standard normals, we get a chi-square distribution. This lends itself well to several statistical procedures, especially ones related to the variance, but also some procedures for comparing categorical variables, such as a chi-square test for independence. So, for example, let's suppose that we want to say something about the population variance sigma squared based on a random sample from a normal population. So one good estimator of sigma squared is the sample variance, usually denoted s squared. So we can calculate this estimator of the population variance, by taking the difference between the observed values yi's minus the sample mean y bar, squaring those up, dividing by n minus 1. Now, you might be asking yourself, why are we using n minus 1 instead of taking a direct average, instead of dividing by 1 over n? Well, it turns out that there's actually a really important reason why we might be doing this. To see why this is a better option, let's find the expected value of the sample variance. So the expected value of the sample variance, which again is 1 over n minus 1 times the sum of the squared deviations. We can pull that 1 over n minus 1 to the front because of the constant. I'm going to distribute that square. Take a look at some properties here, so we'll leave that to the viewer. And it turns out that when you distribute the square and combine some terms, you get this. This becomes the expected value of the sum of the y squares minus n times the y bar squares. So we can distribute the expectation across linear terms. Let's go ahead and do that. Here's what we get. So if we distribute the expectation here, we have the sum of the expectation of y squared. So that's really just the sum of the variance of y plus the expected value of y squared. Same thing here with this y bar squared. That's n times the variance of y bar plus the expected value of y bar quantity squared. Plugging in what we know about how normal distributions are distributed, things start to simplify down. And eventually, we can show that the expected value of the sample variance is in fact the population variance. So dividing by n minus 1 here gives us what's called an unbiased estimator. The expected value of this estimate is the thing that it's trying to estimate. It's the population variance. So that's why we're dividing by n minus 1 when we calculate the sample variance. So another really convenient result that we get here, let's let y1 through yn again be normally distributed. That's going to be a constant assumption throughout this entire video. Then it turns out that if we take n minus 1 times the sample variance and divide by the population variance, that is a chi-squared random variable, or that follows a chi-square distribution with n minus 1 degrees of freedom. It can also be shown here that the sample mean y bar and the sample standard deviation s, or the sample variance s squared, are independent random variables. So there's no correlation, or the covariance is 0 between y bar and the sample variance. So here is where this result is useful. Suppose that the ounces of liquid dispensed by a bottling machine have a normal distribution sigma squared equal 1. We plan to select a random sample of 10 bottles and measure the amount of fill in each bottle. Now, in the previous video, we looked at what sample size would be needed to gain a particular level of accuracy. Now, let's take a look at something different here. So we've got 10 observations that are used to calculate S squared, so calculate the sample variance. We might want to find a range of values that include the sample variance with a high probability. So I might want to find some values, B1 and B2, such that the probability that the sample variance falls into that range is 90%. Now, we don't have a form for the distribution of the sample variance, but we do have a form for a function of the sample variance. Specifically, we know that n minus 1 times s squared over sigma squared follows a chi-square distribution. So I'll take this interval and multiply all of the values in it by n minus 1 over sigma squared. What that does is make this random variable in the center into a chi-square distribution. So now we need to choose where to place cutoffs in a chi-square distribution to get that 90%. Do we want 90% probability all on the left of the distribution? Do we want 95% or 90% probability all on the right? Or do we want a center, 90% probability? If we want the center, or the middle 90% probability from a chi-square, that means we're going to need to remove the lower 5% and the upper 5% from this distribution. We can do this, or we can find that cutoff using the Q chi-squared function. So here we will find the 5th percentile. We'll cut off there. 10 minus 1 degrees of freedom, so 9 degrees of freedom. That means that this quantity, 10 minus 1 times B1 over sigma squared, is 3.325. So that means that our lower range for our lower range for S squared, is 0.394. The upper range, again, we'll take the 95th percentile here, through a similar process, becomes 1.88. So that gives us a range where we think the sample variance will fall in 90% of samples. Now let's take a look at another one of the constructed distributions, the t distribution. So let z be a standard normal random variable, and let w be a chi-squared random variable with new degrees of freedom. So if I calculate this quantity, my standard normal z divided by the square root of a chi-square over its degrees of freedom, w over nu, this follows a t distribution. If you've seen the t distribution before or done a t-test, you're probably thinking that's not what a t statistic looks like, and it's not what we typically see to work with in a Stat 101 class to find the t distribution or do a t-test. It turns out that these are actually equivalent forms. So let's go through that. So we know that if y1 through yn are again normally distributed, we know that the sample mean, or we know that z-scores then, are normal with mean 0, standard deviation or variance 1. We also know that a chi-squared statistic, or w, looks like this. We can take n minus 1 times the sample variance over the population variance. That follows a chi-square distribution. So our t distribution really looks like this. In the denominator, I'm going to replace w with this form of a chi-squared. The degrees of freedom for this particular chi-square are n minus 1. I'm going to calculate a standard normal variable, or I'm going to construct one from the sample mean. So this is my standard normal. Lots going to cancel here. So sigma squares are going to cancel, or the sigmas are going to cancel. The n minus 1s are going to cancel. we're left with s over the square root of n in the denominator, y bar minus mu in the numerator, and there's the familiar form of the t distribution or the t statistic. Properties of this distribution: it's symmetric, it is unimodal. As we increase the degrees of freedom, so as we bump up n minus 1 being the degrees of freedom in this specification, the t distribution gets closer to a normal distribution. In practice, we often use the t distribution for testing, which we'll talk about next semester in Math Stat 2. Let's take a look at an example here. So a forester studying the effects of fertilization on pine forests in the southeast wants to estimate the average area of a pine tree. So he discovered that these measurements are normally distributed with about standard deviation 4 inches in previous studies. So if we sample 6 trees, find the population that the sample mean will be within 2 square inches of the population mean. Now in practice, this t distribution becomes useful when we don't know the population variance, when we don't know sigma, and all we have is an estimate of it s. So we have a small sample, we have unknown population variance, we only have our sample variance s. We'll use a t distribution here to model this. So we want to find the probability that the difference between the sample mean y bar and the population mean mu is less than 2. So we'll set up an interval here. I'm going to divide by s over the square root of n on both sides of this interval to make or build this t distribution. So this is the same as the probability of a t-score between negative 1.223 and positive 1.223. The t distribution again depends on the degrees of freedom. Here that's the sample size 6 minus 1. So our range of probabilities using the pt function to help us out a bit is 0.72. So 72% of samples will fall into that range. Now, how is this affected if we increase our sample size? Let's say that we are doubling our sample size. Instead of sampling 6 trees, we'll now sample 12. Increasing the sample size increases the width of that t interval, so we're moving outward with the t distribution. We have increased our probability. So the larger our sample, the more likely we'll be able to estimate to a certain precision. The last distribution that we'll talk about in this video is the F distribution. The F distribution becomes really useful for us in practice to compare variances. So to compare the variability of sample 1 or group 1 to the variability of another sample. So let's say that we're taking samples of size n1 and n2 from 2 populations with variances sigma squared 1, sigma squared 2. These may or may not be equal. If we calculate S1, or sample variance from sample 1, so S squared 1, S squared 2 for the sample variance from sample 2, these can be estimates of the population variances. We can compare these estimates by taking their ratio, so the ratio of the sample variance in group 1 to the ratio of the sample variance in group 2. Now, it turns out that if these two quantities, or if these two populations are equal variance, so if the two populations have the same population variance, our slightly modified ratio, so if sigma squared 1 and sigma squared 2 are the same, then it doesn't really matter if I add those back in. This turns out to follow an F distribution with n1 minus 1 numerator degrees of freedom and n2 minus 1 denominator degrees of freedom. So if the two populations have equal variances, then the sigmas will cancel out. These s's should be approximately equal as well, so we would expect in that case to see F statistics near 1. So in general, let's let W1 and W2 be independent chi-square distributions with nu1 and nu2 degrees of freedom. Then, formally speaking, we'll define the F distribution by taking the ratio of these chi-squares over their degrees of freedom. So the F distribution is defined as W1 over nu1 divided by W2 over nu2. Now, in order to get from this version of the F distribution to this version of the F distribution, all we really need to do is multiply each numerator and denominator by their appropriate degrees of freedom, and we get those chi-square distributions that we recognize. So these are equivalent. So let's consider the case where we're taking independent samples of size n1 equals 10 from one distribution, n2 equals 20 from another distribution. We're assuming that they're two normal populations with equal population variances. So let's find a value b such that the ratio of the sample variances will be less than that value b with 95% probability. So again, assuming that the population variances are equal, the ratio of these sample variances follows an F distribution with 9 degrees of freedom in the numerator, 19 degrees of freedom in the denominator. In R, we'll use QF to find quantiles from the F distribution. DF1 is the numerator degrees of freedom. DF2 is the denominator degrees of freedom. So we get 2.4 here for this ratio. So for samples of size 10 and 20, there's a 95% chance that the ratio of the sample variances will be less than 2.42. Now, in intro stats, you may have heard a rule of thumb for comparing the variability of two populations. So that rule of thumb was to take the ratio of the standard deviations. So if the standard deviation of group 1 divided by the standard deviation of group 2, if that's less than 2, we typically will assume that populations have the same variance. Now, why does this work? So consider the case where n1 is 10, n2 is 20. We found a limit, or we found a bound for the sample variances. If this ratio S1 over S2 is less than 2, that means that S1 squared over S2 squared must be less than 4. So just squaring both sides of the inequality. The probability of that occurring in this situation is 0.995. So that's almost certain to happen. Again, we're assuming that the variances are equal when we do this calculation. If the population variances are the same, this result is almost guaranteed. So this happens, or this high probability occurs, regardless of the sample size. In fact, if we plot small values of the numerator degrees of freedom on the x-axis, small values of the denominator degrees of freedom on the y-axis, we see in most of these cases very high probability. This does appear to be a bit more dependent on the denominator degrees of freedom on n2 than n1. So that is it for this series of videos covering Math Stats 1. Thanks for sticking around if you've stuck around this long. I hope to see you again soon. Bye now.